Hi guys, in this video we'll be solving the LeetCode daily challenge for August 19th, that is find critical and pseudo-critical edges in min-1 spanning tree. So in this question we have been given an undirected connected graph with n vertices and like they are numbered from 0 to n minus 1 and some bidirectional edges where ai, bi and weight I represent the bidirectional edge between ai and bi with weight I. Okay, and we all know like what is IMST, and in this question we need to find all the critical and pseudo-critical edges in the given graphs MST. So what does a critical edge means? A critical edge means a edge which should always be there in any MST. Like removal of that will cause like to increase the weight of the MST. And pseudo-critical edges are those which are present in some of the MST, but say like if we remove them it doesn't affect much because we can find another MST with similar weight or say same weight. Okay, so what can be our approach here? Okay, let's say we can find the original MST from the graph, okay, using some standard algorithm. Then what we need to do, let's say we have found, and then we will mark one edge like it is if it is not present, then we find the MST again, and let's say if that MST, like the weight of MST is equal, then we can say that this weight like this edge was not critical. No, we can't say that because we can't be sure that this particular edge has been included in some of the MST. But for the critical edges we can definitely say that, because like if removal of any edge can cause increment in the weight of MST, then we can surely say that it was a critical edge. But for pseudo critical edges we need to think something else. Okay, so what can happen for pseudo critical edges? So pseudo critical, it means that like we can remove that. Okay, let's read the definition again. Pseudo-critical edge is that which can appear in some MSTs or at least in one MST but not in all. Okay, so for example in this graph 0 1, okay, edge number 0 and 1, so this means this one and 1 to 2, yeah, this one are the critical edges, while 2 3 4 5 means 2 to 3, this particular edge is a pseudo critical edge. Okay, like finding the critical edge is sorted, no worries in that, but finding the pseudo critical edge is somewhat challenging to me at least. How can we find that pseudo critical? We have to be sure that this particular, okay, yeah, now I got the idea how we can find that. Okay, let me tell you also. Let's say okay, so I will be using the, what to say, that some algorithm is there, na? I forgot the name. It is known as Kruskal algorithms, yeah, Kruskal algorithm. So what is that? It uses a decision certain union data structure, and like the edges should be in sorted order. Okay, edges. So what I will do for finding critical edges, I will just make that we can't edge this part. Like for example, we are searching for the ith edge, whether it is critical or pseudo critical. So check if it is a critical edge, we will just remove it. Okay, and we'll try to form the MST from other edges. And if we can find an MST with us like equal weight, then we can say that it is not a critical edge. And for checking for pseudo critical edges, what we will do, we will just add this edge like beforehand, and then we will check for the other edges, and if we can form the MST with say this particular like the same particular weight, then we can say that this edge is pseudo-critical. I think yes. I still I guess some issues there. Let's say we add some edge, so it means like it is present in this particular MST. It is present in this particular MST, and we can form an MST with including this edge, so it means that it can be a critical also. Okay, so if it is possible to form a MST by adding it and by removing it, like if both conditions satisfy, say adding it and by removing it, if both of these conditions satisfy, can we say that edge is a pseudo critical edge? I guess yes. Yeah, we can say that. So yeah, I guess we can proceed. So first of all, say we define a DSC class, so it will be of n private and a parent array is there, a rank array is there, and the constructor will be there for DSC with n. So n will be nothing but okay, and this dot pair will be named n, and this dot rank also would be named 10. Okay, and now for all the rank array, we'll be making rank of I equal to pair of I equal to I, and for getting a particular say parent of any node, say pair or find. Okay, is node, so if pair of node equal to node, we will be returning node, otherwise we will be using the path compression. So pair of node will be find of pair of node. Okay, and say we use public boolean union to merge u and v edges. So firstly finding the leader or say representative of u with element, find of u and v of find v, and if u and v are equal, we will simply return false because they belong to the same component, and otherwise if rank of u is greater than rank of v, we will be making pair of v equal to u. Otherwise, if we will check if rank of v is greater than rank of u, then we will make pair of u equal to v. Otherwise, we will make anything, say pair equal u equal to v and rank of v plus plus, and we will simply return as true. So DSU class is implemented. Now what we need to do, first of all, say edges we have now. So for int I equal to 0 to I less than edges dot length, we will make edges of I, like we will make some modification in the array. Edges of I, okay, edges I0, edges of I1, edges of I2 and I, representing the number of edge, and then we will sort it based on the weight. Edges, say new comparison, and public int compare, and we will be returning based on weight only. So h2 minus v2 y2, sorry. Yeah. So the edges are also sorted. Okay, now say just define the answer list of integer, say answer no array list, and answer we will be adding two empty list. Okay, now for every edge. Okay, firstly defining okay, finding MST. Okay, let's say we define a DSU with n particular edges, or sorry, and size. Okay, and then we will find int wt equal to find mst with this DSU and edges. Okay, it will return, say, private int find mst DSU and edges. What it will return? It will return the weight of MST, like within this DSU structure. Okay, so say int weight equal to 0, or otherwise let it be edges of, yeah, and if DSU dot union x0 x1 weight plus equal to x2, and we will be returning a weight. Return. Okay, yeah. Now for all the edges, what we have to do, let's say we will define this DSU again every time, and now what we will check is if it is possible to make a MST again without using this edge and using it edge. So first of all, let's say without using. Okay, and also pass a -1 here, int, okay, so -1 int not to take. So this should be inside it, and say int is there, and if int plus plus is equal to not to take, then we will sorry, not return, we will just continue. So without using this edge, say int wt1 equal to find mst DSU edges, and say I. Okay, and again a DSU will be initialized, and say using this edge. Okay, so int wt2 will be, okay, using this edge means DSU dot union edges dot I 0 edges I1, and wt is equal to edges I2 plus find MST from the remaining edges DSU edges and -1 again, because now all of the edges we can take, and we will be not be taking the same edge again because we know that we are checking from the union function. Okay, so if wt1 is not equal to wt2, then we can say that this is indeed a critical edge. So answer.get 0 add edges of I and 3, because this is the initial index. Okay, and if wt1, okay, pseudo-critical edge means, okay, wt1 is equal to wt2, wt, this should be also wt, and okay, if we can form MST by using this edge and like without using this edge and using this edge also, okay, then we can add it edges I3 edges, and we can return our, say, ans. I guess it should work. Okay, just a semicolon. Anything else? Again, cannot find a simple. Okay, I misspelled digest. Okay. So many compilation errors are there. Okay, so for two cases it worked. Let's try if it is working for all the cases. Yeah, it works and we are beating 80% of the summations. So now let's discuss something on the time complexity. Okay, so we know that Critical works in, say, order of n log n plus n, okay, or say alpha into n, where this say this n is number of edges and this alpha is inverse Ackermann function. Okay, inverse Ackermann. So this alpha value will be less than equal to 5 for all the n's greater than equal to, sorry, for all the n's less than equal to 10 power 600. So instead we are having n equal to 100, so this alpha will be somewhere around 2. Okay, now so this n log n comes from where? It's come from sorting digest. So how many times we are sorting? One time. So n log n plus or maybe say not with n, so say e log e log e plus how many times we are okay, how much time is required to find mst e, and how many times we are finding it again? 2e, so 2 into e square. So this is our overall time complexity. And okay, 2 into e square. And what can be the maximum value of e? 200. E can be 200. So let's see how many, like, theoretical number of operations we might be doing is 200 into say 8 plus 2 into 4000, 1 2 3 4 1 2 3 4 40,000. Yeah, 80,000 plus 16,000, 80,000 plus 16,000. So you can say that we are roughly doing 10 power 5 operations. Okay, that is anyway acceptable. So I don't think like a better solution exists, at least in my knowledge, even though there might be some graph theory techniques, like mostly theoretical, that can be implemented here to find the answer. Okay, but one need to be very well in the graph theory to understand them. Let's see the solution also, if there is something simple solution. Okay, they are doing the same only. Okay, okay then, so thank you for joining in. This was all for the video.